When you look up at the night sky, you are literally looking back in time. Because light takes time to travel across the vastness of space, we see distant stars exactly as they were years or millions of years ago. To get the best look at this ancient light, we've historically relied on the Hubble Space Telescope. In 1995, scientists pointed Hubble at a patch of sky that looked completely empty. They let it stare at that same dark spot for days, collecting as much light as possible. The result was a stunning image filled with thousands of distant galaxies where we thought there was absolutely nothing. Hubble has been incredibly successful, but it also has a crucial safety net. It orbits just 540 kilometers above Earth. When things broke down or parts needed an upgrade, NASA could send astronauts up in the space shuttle to crack it open and make repairs by hand. But Hubble has a physical limit based on how our universe actually behaves. Space is constantly expanding, which means distant galaxies are accelerating away from us. As the light from those galaxies towards Earth, that expansion physically stretches the light waves. What starts out as a compact, visible light wave gets stretched out until it drops completely out of the visible spectrum and becomes infrared light. Astronomers call this the Doppler effect, or redshift. To capture that stretched ancient light, you need an infrared telescope. The catch is that infrared instruments are highly sensitive to heat. If you put an infrared telescope in low Earth orbit, the ambient heat from our planet and even the heat from the telescope itself would completely blind the sensors. The only way to keep the instruments cold enough is to park the telescope 1.5 million kilometers away in the freezing darkness of deep space at a gravitationally stable spot called the L2 Lagrange point. But at that distance, it is completely out of human reach. There is no shuttle, no repair crew, and no safety net. Every single piece has to work perfectly on the very first try. Capturing those faint, distant infrared signals requires an incredibly large primary mirror to act like a giant bucket for the light. The immediate problem is that a mirror big enough to do the job wouldn't physically fit inside the payload fairing of any existing rocket. Engineers solve this by dividing the primary mirror into 18 separate hexagonal segments. They cast these out of beryllium, a rare element that is incredibly lightweight and holds its shape perfectly in extreme cold. By using a segmented design, the outer edges could be folded back on hinges to squeeze inside the rocket for launch. Each of those beryllium segments is coated with a microscopic layer of pure gold. Gold is a highly efficient reflector of infrared light, making it the perfect surface to bounce those ancient signals directly into the telescope sensors. Even a million miles away, the telescope still needs massive protection from the sun's glare. The base of the structure features a 5-layer sun shield, roughly the size of a tennis court. Each layer is about as thin as a human hair, designed to permanently shade the instruments and keep them at operating temperatures near absolute zero. Before it could leave Earth, the hardware had to prove it could survive deep space. The assembled optical instruments spent 100 days sealed inside Chamber A, the world's largest high vacuum chamber. They sucked all the air out and plunged the temperatures down to freezing extremes to verify the electronics and mirrors wouldn't warp or fail. Getting to that point required an immense global effort. It took 30 years, $10 billion, and the coordinated labor of thousands of scientists across NASA, the European Space Agency, and the Canadian Space Agency. Once fully assembled, the incredibly fragile telescope was packed into a specialized climate-controlled shipping container called STARS. Instead of flying, it took a slow-moving, highly precarious journey by cargo ship down the coast of California and through the locks of the Panama Canal to reach the launch site. The James Webb Space Telescope finally met its ride to space on Christmas Day 2021. It sat atop an Ariane 5 rocket at the Guiana Space Center in South America, a launch vehicle chosen specifically for its proven track record with delicate payloads. Surviving the violent shaking of the rocket launch was a massive relief, but it kicked off an intense month-long cruise to the L2 Lagrange point. During that transit, the telescope had to deploy itself autonomously in the dark. The deployment started with extending the solar array to secure a power source. Then came the highest risk phase, the tennis court-sized sunshield slowly pulled its 5 ultra-thin layers outward and tightened them without snagging or tearing. Finally, the mechanical wings holding the side portions of the primary mirror swung forward on their hinges, locking precisely into place to complete the giant golden hexagon. Over those few weeks, hundreds of individual mechanisms had to move in sequence. If a single pin failed to drop or a single cable jammed, the entire $10 billion mission would have been useless. No astronaut could reach it to fix the problem. Once it arrived and successfully unfolded, engineers spent weeks on a process called mirror phasing. They made microscopic adjustments to each of the 18 hexagonal segments, perfectly aligning them so they functioned together as one flawless eye. The payoff for that massive logistical gamble arrived in July of 2022, when Webb transmitted its first fully processed high-resolution images back to Earth. With older telescopes, thick clouds of cosmic dust blocked our view of the star formation inside. Because Webb gathers infrared light, it peers right through that dust, exposing the glowing, newly forming stars that were completely hidden from us before. By capturing infrared light in deep space, Webb bypasses the physical limits of previous observatories. We now have a 20-year window to look billions of light-years away,